I came across this blog post by Murat. I believe is his name. He has a blog where he publishes a bunch of usually research paper reviews, but he also does general distributed systems articles. And in this article, the TLA plus one, the one we're about to talk about, he basically goes through what I would consider to be a pretty clear and concise specification. He's able to distill the core essence of what the core bug was in the AWS outage. Now, I should mention that his article is actually based on a prior article by somebody else who essentially did the same thing, but using a different specification language called Promela, Promela, Promela. And so in this prior article, there is also an exploration of the race condition that was supposedly the core issue behind the outage. And so with Promela, you have the model checker called Spin. With TLA Plus, you have the TLA Plus spec language, and then you have the TLC model checker. So in Murat's blog post, he does the TLA Plus and TLC spec. What I took from that blog post, because it felt so simple and straightforward, I essentially decided to do a translation in FizzBee, which is another formal specification language. I don't think FizzBee has a, how do I put it? I think the language FizzBee and the model checker, well, FizzBee is both, I believe, a specification language. So there's the language and then there's the actual model checker. And I think both together are dubbed are called FizzBee. I don't think it's like with TLA Plus where you have TLA Plus and then the actual model checker TLC. I think with FizzBee it's just kind of both at the same time. So yeah, so I decided to go through and to go and do a translation of the TLA spec. And so we are going to go through that. Now, in order to essentially set the stage, we can do a quick read of one or two paragraphs that I think does a good job of setting the stage for why you will even want to spend a little bit of time doing some state machine modeling to get a good representation of what went wrong. Let me see. Okay, I guess we can just take it from the top, right? So it says AWS published a post-mortem about a recent outage. Big systems like theirs are complex, and when you operate at that scale, things sometimes go wrong. Still, AWS has an impressive record of reliability. The postmortem mentioned a race condition, which caught my eye. I don't know all the details of AWS's internal setup, but using the information in the postmortem and a few assumptions, we can try to reproduce a simplified version of the problem. As a small experiment, we'll use a model checker, right, to see how such a risk could happen. Formal verification can't prevent every failure, but it helps us think more clearly about correctness and reason about subtle concurrency bugs. Of course, writing about it after the incident benefits from hindsight. We already know what went wrong. For this experiment, we'll use the spin model checker, which uses the Promela language. All right. There's a lot of details in the postmortem, but for simplicity, we'll focus only on the race condition aspect. The incident was triggered by a defect in DynamoDB's automated DNS management system. The components of the system involved in the incident were the DNS planner, the DNS Enactor, and Amazon Route 53 service. I will say that from here on, you should keep those names in mind, because we're gonna keep referring back to those labels, right? The planner, the Enactor, and then just the service, which stands for the Amazon Route 53 service. So I guess this is the core description of what essentially went wrong, or as far as the very compressed description of the system, right? So the DNS planner creates DNS plans, and the DNS enactors look for new DNS plans and apply them to the Amazon Route 53 service. 3 enactors operate independently in 3 different availability zones. My understanding of how the DNS enactor works is as follows. It picks up the latest plan, and before applying it, performs a one-time check to ensure that the plan is newer than the previously applied one. Let me see if I actually need to go. I wasn't planning to actually read as much as I just did. So we'll just kind of pause it here, but essentially what you should retain as far as setting the stage is that what we're about to talk about involves really 3 main components, right? So we have the planner, you have the enactors, and you have the actual service. And another key thing to keep in mind is the fact that there is no consensus or no communication between the enactors at all, right? And this is essentially where the root of the problem comes from. The idea that you have, whenever you're dealing with distributed systems, coordination becomes something to watch out for. All right, so I think that we kind of are at a point where we have some introduction of what we're about to talk about. So again, you can look at the original TLA spec that Murat put in his blog post. It's pretty straightforward, which in fact is what motivated me to quickly put together a FizzBee version. There's also obviously the original blog article. Again, I'll put the links for both articles in the description, right? So that you can check them out. So there's also the original Promela specification. And now we'll go over our own version, the FizzBee version. By the way, this is the FizzBee online playground editor. It basically allows you to quickly prototype stuff without you having to install anything on your own machine. right? This is the link. And so on the, just to kind of give a brief introduction, I guess, of the tool itself. I mean, it's pretty straightforward. You have the text region or window, and then on the right side you have the let's call it the trace viewer, or the quote-unquote debugger. We can call it we could call it a debugger if we wanted. And if you look on the right again in the debugger section, you will see that there's already a trace, and this is because I mean this is the result of running the simulation of the model the model that is spec'd out. And just, I guess, spoiler alert, we are able to reproduce the TLA spec from Murat's blog, and we get the same outcome, which is that an invariant is violated. So let's actually go through the model itself. So we start off by defining our constants. We have the number of enactors, the threshold that allows us to have some sort of cutoff for when we can discard plans that have been generated and either just became stale or were applied at some point in the past. So just from that, one thing to keep in mind is that just because a plan is generated doesn't mean that it will necessarily get to be applied. And so the threshold applies both to plans that have been applied, but also plans that have been generated but have been, I suppose, just pending for a certain time. And so this is basically a way to truncate the sequence of plans that have been generated by the planner. And for the sake of modeling, we are setting a max plan, meaning the maximum number of plans that will be generated as part of the simulation of the model. Okay, I was just double checking because I just realized I didn't do a quick audit of the sound. Hopefully this is coming out just fine. Otherwise I'll just have to redo the whole thing. Hopefully not. All right, so we start with the planner, right? So in FizzBee, you have this ability to actually be, it allows you to model different roles in your distributed system, which is specifically for a system like this where we have different actors. This is really convenient. It's a good way to structure the specification. So we have the planner role, right? On initialization, we initialize essentially the cursor for what is the latest plan that's generated by the planner. We keep an audit of all the plans that have been deleted due to the plan age threshold, cleanup, let's call it routine or directive. And so initially we fill in the list of deleted items, and we can do that because we know that at most we'll have 5. And so we go ahead and just fill that in, and we set all of them to false, right? Because we're just getting started. Nothing's deleted yet. Channel here, you can think of channel as just a queue, right? The queue of plans that are generated by the planner. And the planner really has one key action, the enqueue action, what it does is it essentially first checks if we have reached the maximum number of plans that we want to generate as part of the simulation. If not, then we essentially generate another plan by incrementing the cursor for what the latest plan is, and we enqueue into the channel. Now, if you're not familiar with FizzBee, atomic is basically means that it's like, think of it as a database transaction. It's all or nothing, right? If we didn't put atomic here, it will make, by default, that means the action is serial. Now, the difference between atomic and serial is that with serial, it's possible, at least from a modeling perspective, it's very possible that between the execution of this expression here and this one here, something else can interleave, right? Maybe there is a dequeue operation from an enactor that happens in between these two expressions. So that's what serial means. It means that you can have some interleaving happening with other system components, right? It's a matter of concurrency, essentially. And the fair means that, so there's different levels of fairness. I don't think we need to really go into the details of that. But the idea of fairness here is that if you have an action that is, I think the way it's explained is that if you have an action that is continuously enabled, then it will be continuously executed. It's in a very simple way. A simple way to put it is that you're essentially not starving that particular action. That may not be a very precise and very correct explanation, but essentially the fairness here is basically saying, well, if this action is enabled, and by enable we mean the predicate, if there is a predicate that, like the one we have here, right? If there is a predicate and that predicate allows for the execution of the function, then eventually the scheduler or the simulator, in this case, right, the model simulator will let that action execute. Again, you can look at the FizzBee documentation online where they have a really good explanation of the different levels of fairness. I don't think we need to really delve deep into that particular feature of the language. All right, so I believe we are done with the planner, right? So there's the initialization and then there's the enqueuing, right? Now for the enactor, so there are really two main things, or I guess state variables for the enactor. It's keeping track of its own program counter and whichever plan it's currently processing. And by default, right, when it gets started at initialization, both are set to 0. And we'll see how the value of the program counter affects the remaining actions of the enactor. So first action is the dequeue operation, right? An enactor will dequeue from the channel of the planner, or the channel that is containing, serves as a container for the plans that are generated by the planner. So it's going to dequeue, it's going to dequeue a plan, well, assuming that the queue is not empty, right? That this is what we're checking here. We're checking that the queue is not empty and that the program counter is set to 0. Now, maybe I should just go ahead and straight up lay out how the program counter affects the actions of the enactor. So there are really three possible values. There's the 0 value, 1, and then 2. 0 means that we are at the beginning of the full sequence of actions that a enactor will take as it's going through and processing a particular plan, right? So there's a sequence of 3 actions. There's the DQ operation, there's the apply operation, and there's the cleanup operation. And we have a program counter value for each one of them. So for the first one, it's 0, so it's 0 indexed. So DQ corresponds with 0, apply corresponds with 1, and cleanup corresponds with 2. And you will notice that on entry of each of these actions, we check that the corresponding program counter, or the current that the current that the current program counter is the appropriate value for the action that we're about to run. So again, for apply, it will be 1, and for cleanup, it will be 2, right? Okay, so for DQ, we check that the queue is not empty, and we check that the program counter is set to 0. So we are at the very beginning of our sequence. So it DQs, right? It takes the head, right? The plan that is at the head of the queue, and it updates the queue. Well, dequeuing essentially, you're updating the queue from a state tracking perspective, and it sets the program counter for the next action, which is apply. And again, in apply, notice that all of these actions are atomic, right? This is very important, right? Because we are indicating the fact that we expect all these actions to happen, atomically, like a database transaction. It's all or nothing. And this is a key aspect of that allows us to understand why what happened. Okay, so we are on the apply. Again, the apply action of the enactor. We check for the proper program counter, and this is very important. Before we apply a plan, again, and this is actually one of the most critical parts of this whole specification. Before an enactor applies the plan that it DQ'd, it needs to check that the plan, in terms of the global state of the system, it needs to check that that plan, for whatever reason, hasn't been deleted, right? Because you don't want to apply a plan that has been deleted. I mean, that should be pretty obvious, right? So it checks that the plan that it has is not stale or hasn't been deleted, whatever you want to describe it as. And if the check passes, it sets the current plan to be, the plan that it DQ'd or that it's holding on to. And then it also sets what is the highest plan that has been applied so far. Now, I guess we haven't come across the highest plan variable. It's a global variable in the global initialization action. So obviously the current plan is, whatever current plan is the configuration for the AWS Route 53 service. And the planner generates plans, over time. And the implicit understanding here is that each plan has a version or some sort of timestamp that indicates that you have some sort of ordering, right? One plan is newer than another one, right? And so we have the latest plan, which is the latest plan generated by the planner, but then you have all the plans that have been generated before. And so there is some there is the implicit understanding that there is some ordering, right? Now, as we are applying these plans, we want to keep track of which, because of the lack of coordination, just because a plan was created at first, right? Let's say you pick two plans, right? One is generated at time 1, the other one is generated at time 2. Just because you have, there's no guaranteed, there's no guarantee that the plan 1 will always be applied before plan 2. And again, this is a result of the fact that there is no coordination between the enactors, right? And so again, there's no assumption that the earliest plan generated will execute before the latest plan executed. And so this, as we're thinking about the system, it's important for us to not conflate both, as whatever the current plan is versus the the version, or the latest version. Yes, the current plan is not necessarily the latest or the oldest generated plan. Anyway, the point is that we need to keep track of, have an idea of, in terms of versioning, which plan has been the I'm missing the right words to use here, but I hopefully you kind of have an idea of why we need the highest plan applied variable. We're gonna move on. I don't want to get stuck on that, but hopefully you kind of get the gist of what this variable is about. We set, again, moving on, we set the program counter to the next step, which will be the cleanup action. Also, when we check that the current plan, or the plan that we've dequeued, when we check that that plan has not is deleted or not, right? There are obviously two options: either it's deleted or it's not. If it's not, then that's the quote-unquote happy path. The alternative is, the plan that we are hoping to apply actually has been deleted. That means that essentially it's a no-op. We don't have anything to do, or we shouldn't do anything, right? We should not be applying a plan that is essentially expired. And so this is the branch that represents this, and we essentially reset things to the initial state. All right, now we get down to the entire system's initialization action. Again, we have the current plan and the highest plan applied. We set those to 0, right? Then we initialize our planner, we initialize our enactors. For the purpose of this simulation, we only need 2. The number itself doesn't matter specifically. We just need at least 1 to showcase what the issue is. And at the bottom, right, we have our properties, our system properties, at least the ones that we care about. So when it comes to, if you're not familiar with this kind of programming slash modeling, when you're doing the specification for your state machine, there are really two kinds of properties that you want to be expressing. You have the safety properties and the liveness properties. Now the difference is that with the safety properties, you essentially saying these are things that should not happen. And I think the way it's usually put is that you have the things that are simply bad, like you do not want this to happen ever, as the system is, as part of the system's behavior, this particular thing should not happen. And in the case of what we are modeling here, and this is in plain English here, right? The currently active plan must never be marked as deleted. That's the safety property that we are after here. And it makes sense, again, why, again, thinking about the fact that we are talking about AWS Route 53 service, a DNS service, you definitely don't want the current plan to be deleted. Otherwise, you end up having a bad day, just like what actually transpired recently at AWS. And the way we assert for this property is that we check that either no plan is generated, essentially, right? Then nothing actually, the planner has done no work, and in that case, then it's whatever. Or for any plan that's generated, when it becomes active, it should not also be marked as deleted. And let me see. Okay, and this was not in the original TLA spec from Murat's blog post. From his blog post, that was not in there, but I just figured I'll add it just as a way to show how to set a liveness property. Oh, I guess I didn't really speak to what a liveness property is. Liveness really is saying something good will eventually happen, which really, a very simple way to put it really is that progress will be made, right? If you think about a scheduler, right, a job scheduler, a liveness property is the scheduler eventually schedules a task, right? Something good happens, something good eventually happens, right? Again, going with the example of a scheduler, a safety property would definitely be no task gets deleted, or no active task gets deleted, and that's terrible. But you get the point. It's easier to usually come up with a safety property than a liveness property, I think, generally speaking, because it's easy to really think about, okay, what are things that we definitely never want to see happen in the system. With liveness, you kind of have to be a little bit more deliberate, really think about what liveness means for your system, right? Because if you pick it wrong, you can actually end up focusing on the wrong thing entirely, or you can even end up picking something that restrains how your system could work or perform, right? So anyway, liveness is a little bit trickier to come up with sometimes, I think, generally speaking. Safety properties that tend to be a little bit more straightforward, right? You just really want to think about what is it that I never want to see happen in the system. All right, so that was the entire spec. Again, it's a part of the TLA Plus version. I hopefully going through this, you have an idea of what's happening, right? And when we run the model, we are able to reproduce what the issue is. And I guess the way to really put it is that it's a typical risk cognition problem, right? And essentially you end up in a situation where you have an enactor that dequeues a task, or a plan, essentially sits on it, while another one dequeues one plan, processes it, dequeues another plan, processes it, and then it gets to its third plan. Again, the first one is still sitting on that very first plan that it dequeued. Hopefully you see where this is going, right? So the second enactor is now on its third plan that it dequeued, and it's going through that process. And at some point, right, enactor 1, which again is still on plan number 1 that it dequeued, is going to do something from its perspective that is no longer valid, right? Because this enactor is holding on to, it doesn't really have, again, there's no coordination between the enactors, remember. So it's now performing an action, or its actions, from essentially a localized view of the world, right? It doesn't know that enactor 2 has already gone and processed 2 separate plans, and now is on its third. And so this is where you can get into very bad situations, right? Because there's no coordination. And the key thing here is that you end up in a position where enactors can do things that essentially overwrite each other's actions. Because again, there's no coordination. They don't know about each other, right? And so they can easily end up stepping over each other's work, and that leads to bad outcomes. I think in the article from Murat, hope I'm saying that right, by the way. Murat. I hope I'm saying that right. I'm sorry. Okay, let's see. Yes, okay, the trace goes as follows. The planner issues several consecutive plans. Enactor 1 picks up 1 but lags on the next 2 steps. Enactor 2 arrives and moves faster. It takes the next plan, applies it, and performs cleanup. Because the staleness threshold isn't yet reached, Enactor 1's plan survives this cleanup. On the next round, Enactor 2 gets another plan and applies it. Only then does Enactor 1 finally execute its apply step, overriding Enactor 2's newly installed plan. When Enactor 2's cleanup runs again, it deletes that plan, which is now considered stale, violating the invariant never delete active record. And that's exactly what we are able to reproduce here, right? We have the planner that enqueues, the planner that enqueues 1, 2, 3 tasks, right? Back to back. It doesn't really matter that it's back to back, but 3 plans generated by the planner. Then Enactor 1 does a DQ, but then it essentially sits on it for whatever reason. Some performance issue, some network link that wasn't working right, something. The machine literally crashed and it's being restored. Something happened that caused Enactor 0, right, to just kind of sit on the plan that it DQ'd. Well, while that's happening, Enactor 1 does a DQ, right? It applies the plan and it does its cleanup. Then again, Enactor 1 goes back, right? It does another DQ, it does another apply. And it's when it's on its second apply operation, that's when Enactor 1 comes back to life, essentially saying, oh, I'm still alive, and I have work to do, right? Except the work that it's about to do is about to screw things up, right? Because when it applies its plan, right, because it's been sitting on plan 1 that it DQ'd a long time ago, it doesn't know that Enactor 1 is now essentially processing the third latest plan generated by the planner, right? And even though Enactor 1 applied the third plan, right, the third latest plan by the planner, Enactor 0 essentially is going back in time and applying the very old first planner. The very old first plan that was generated by the planner. And it's setting that as the current plan. Well, that's a problem because when Enactor 1, again, which is oblivious to the fact that Enactor 0 just set the current plan as 1, right? It goes ahead from its perspective, that current plan is 3, right? So it basically goes ahead and it says, remember the threshold, the age threshold is 2. Okay, so it says, okay, so the current plan is 3 from its perspective, Enactor 1's perspective. The current plan is 3. The staleness threshold is 2, which means that 3 minus 2 is 1. So any plan that has version 1 or lower, in this case that shows version 1, because the number of plans are 1 indexed instead of 0 indexed, but that detail doesn't matter here. So Enactor 1 thinks that current plan is 3. The staleness cutoff is 2, so it does 3 minus 2, and it basically lands on the fact that any plan that is 1 or version as 1 or lower needs to go, right? And what does that mean? It essentially deletes plan 1 as a result of that calculation. But why is that a problem, right? This is a problem because just a few moments ago, right, Enactor 0 set the current plan to 1, right? So Enactor 1 is going about its cleanup as it should, and it has decided that plan 1 or lower needs to go. It's oblivious to the fact that Enactor 0 actually set the current plan to 1. And so you end up in a very situation that you said you don't want, which is that a current plan is deleted. And that is how AWS ended up having a very, 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 very bad day. And this is a good example of how formal methods, formal specification can really, really help you discover Heisenbergs, right? Heisenbergs. Weird issues, right? Especially relating to race conditions, concurrency, coordination protocols, all that good distributed systems stuff, right? A tool like TLA Plus, a tool like FizzBee, a tool like Promella, right? Paired up with some model checker can really help you get ahead of the kind of this kind of bug that AWS just had to confront or deal with. And so this should be a good exercise in I guess getting into the habit of thinking about formally specifying the systems that you're working on, systems or protocols. Just really anything, I guess, if you agree with Leslie Lamport that really any computing device comes down to essentially being a state machine, then it's a good idea to be able to just really think about that state machine. And a way to do that is to use formal specification languages like TLA Plus and FizzBee. FizzBee is more recent, right? It's supposed to be a more approachable, from a developer's perspective, a more approachable spec language than TLA Plus. TLA Plus is a more established spec language. Again, it was made by Leslie Lamport, so definitely something worth checking out. And yeah, again, I will put links to the blogs, the blog posts in the video descriptions. You should go ahead and read the articles for yourself, and maybe also, on your own, try to re-implement the TLA spec. Well, first of all, if you've never read or written TLA Plus, this is a really good opportunity to try it out, right? You can install it and just literally copy paste what he has here. I think he included a link to the spec in a GitHub repository. So you can, let me see. Yep, it's still here. Okay. So again, if you've never touched TLA Plus or you don't know anything about it, this is a really good entry point for you to just copy the code and play with it. Just kind of get an intuition of things. Some of the syntax gets a little bit it's an acquired taste, but once you do, it's fine, right? For example, this line here, right? The delta sign here is basically saying the next value for Enactor PC, which is the program counter, is going to be all the, it's taking the map of all the existing Enactor program counters, and it's only updating the one for the current Enactor, right? So the syntax, it's an acquired taste, but it works. Like it's a good thinking tool, as Leslie Lamport would put it. All right, so I think this is it. I think I've said everything that I wanted to say about this. Hopefully this was interesting to you. Hopefully this gets you curious about exploring the use of formal specification languages. I would definitely suggest that you either try TLA Plus or FizzBee if you want something that is, again, easier on the eyes or more, in terms of syntax, feels more familiar, right? One of the supposedly selling points of FizzBee is that it has this Pythonic feel to it, and I mean you can tell just by looking at the way it looks, right, from a syntax perspective. And I think it's specifically Starlac, which is another Pythonic language. I think it's mostly used for, I think Bazel, the build tool, is in Starlac, right? Language. Yeah, okay, Starlac, formerly known as Skylark, is a dialect of Python. Yeah, for configuration language. Yes, and Bazel. Yeah, I know stuff. I remember things. So yeah, the Starlac language. I think FizzBee is specifically using the Starlac syntax, which again is as we just read, is a dialect of Python. So maybe you don't necessarily want to, you're not necessarily ready to jump in and really sink your teeth into the syntax of TLA plus, and maybe you want something that's a little bit, that feels more familiar, then FizzBee will be a good choice. I think there's also a Quint, which I think also has a Python like syntax to work with. Let's see, on the 5-minute guide. Yeah, so you'll see, it has action, you can set variables, constants, It also has that feel of, the syntax is more developer friendly, essentially, which is not, I don't think you can necessarily say the same with TLA plus. But again, I hope that this is a good entry point for you into the world of formal specification, and I'm interested to hear what you think about this whole thing, and maybe reading through the article, right? The articles gives you a better idea of what happened with the outage, because I believe there is a bunch of postmortem, logs and audits or whatever that I think AWS published, which obviously you can read through, but I think this is a good, more, compressed explanation that makes it obvious, makes obvious what really happened. Anyway, thank you for watching this, and if this was, again, useful, please like and subscribe. I'll see you in the next one.